I'm going to be talking about using Simulink in order to estimate the power of a signal in different frequency bands in the presence of noise. And so if you have a signal that over time contains the same frequency information or is stationary, but you have random noise introduced throughout time, you can use certain techniques in order to better estimate the power density of that signal. And so I'm going to be using MATLAB and Simulink in order to run a simulation for this and show some results. So here I've set up a system with a sample rate of 1 kilohertz, and I've set up a sine wave with a frequency 100 hertz and an amplitude of 1 volt. Also, I'm going to be introducing noise. It's going to be Gaussian noise with a standard deviation of 0.5 volts. Now, in hardware, often processing is done with frames rather than samples. So hardware will read in some number of samples, and we'll call that set of samples a frame. And so in Simulink, often it's useful to use frames instead of the samples concept. And so what I'm going to be doing is I'm going to be comparing single FFTs throughout time to what we call a time-averaged periodogram, which basically takes many FFTs, finds the power of a signal, and averages it over many instances or over many frames. So here I've just set the number of frames to look at to be 50 frames, and the number of points in my FFT that I'm going to be computing is going to be 256. And so if we have 50 frames, each with 256 samples, we're going to have a total number of samples that is the multiplication of the two. And then these two lines here are just constructing frequency axes for plotting later on. And this variable here, an average, is going to be the number of frames which I'm averaging in my periodogram. So I'm going to run this block really quick, and then I'll take you to the Simulink model. So here in the Simulink model, you can see that we have noise, and we've given the noise 0 mean and standard deviation sigma n. We have a sample time, which is the reciprocal of the sampling frequency. And then the number of samples per frame is going to be the number of points that I desire in my FFT computation. Also, we have our ideal sine wave with amplitude A, frequency F1, and again, sample time is the reciprocal of the sampling frequency, and the number of samples per frame is going to be the number of FFT points. Now notice that up here we do not have, or we still have a stopping time, but I'm defining my stopping time to be the number of total samples that we're taking divided by the sampling frequency. Or another way to do that would be the number of total samples multiplied by the sampling period. So what that's going to do is basically give me enough sample points to construct the number of frames that I specified in my script. So once we have these two signals together, I'm going to route first the ideal sine wave to this block over here, the 2 workspace block. That's just going to output the signal to my MATLAB workspace so I can access it later and plot it. And then what I'm doing here with this Welch block or periodogram is what that's called. This is going to compute the periodogram of the sine wave that we have. So what it's going to do is, if we open it up, it's going to use some kind of window on the data. Here I'm just using a Kaiser window with the beta value of 5. It's going to compute either one of these two quantities. I have it set up to compute the mean square spectrum. So what that's going to do is it's going to take several FFTs of consecutive frames of data, and here I have specified it's going to take n average frames, and it's going to compute the FFTs of those each individually. It's going to find the magnitude of them and square it to get the power, And once it has that, it's going to divide by the number of frames that we're using. So you're going to get an average, basically power spectrum of your data. And again, the FFT length is going to be number of FFT points that I want in my calculation. So for each frame, we're generating this number of points, and we'll be computing this length FFT. And so that's going to output a spectrum with the number of FFT points coefficients, but that spectrum is going to be symmetrical since we're looking at power, especially there's no difference between the left side and the right side of the data because we have no difference in phase. And so all we really need to look at is 1/2 of the spectrum. Now the way that this spectrum is output, just like the FFT command in MATLAB, the first component that we'll get out of the periodogram function is going to be the DC reading. And then from there, we're going to get the positive frequencies half of the spectrum. Once we're at number of FFT points over 2, halfway, then it's going to start at the negative frequency end and work its way back towards DC. So it's kind of a weird ordering, but what we're going to do is just slice out half of those values, and that's going to be done using this selector block, this one right here, signal routing. And so the selector block is going to basically take, it's going to take some starting index, which we're going to say start at the first index of the sample, the DC value, and output number of FFT points over 2 samples. So this is just going to take basically from sample 1 to n FFT over 2 and slice those out and pass those along to our output to our workspace. And as a side note, these dimensions that you see here are often very helpful. So it allows you to make sure that the data that you have is interfaced correctly. And how to get those, let's see if I can find it. I believe it's in debug, information overlays, and then signal dimensions. So if you click that and you run your model, then it should show you the dimensions of the signals being routed everywhere. So you can make sure that the signal output by one block matches up with the required input for the next block. And so going on up here, now that we've looked at the ideal sine wave, we're going to add the noise to the sine wave, and that's done with this sum block right here. So it should be this block, and we don't actually need to change anything right now with this block, but you can change the signs that you want in this block. So we want 2 inputs, and they're both going to be added. You can change one to a negative sign and it'll subtract that, but for now we don't want that. And so now what we have here is this spectrum analyzer block. So that would be this first one. And what that block does is it basically computes its own FFT over some number of samples and shows you the spectrum of the signals. So what we're going to be looking at here, I have the ideal signal routed to this, and then I also have the signal plus noise routed to this. And you can ignore this comment right here. So now again, we have the signal plus noise. We're going to repeat the same thing up here that we did down here. And again, I have it set up the same way, Kaiser window, using this many points in our FFT, this many averages for the power spectrum, and then slicing out, again, that first half of data points. So this is going to accumulate n average different sets of samples and compute their FFTs. Now this line down here is just going to compute a single FFT. And so we can see here I have the FFT length set to n FFT, and I've also selected to divide the output by the FFT length, which is going to normalize the output. And so we're going to compute that FFT, take only the positive coefficients, and then output that to the workspace. And so if I run this from here, we should see that spectrum analyzer is going to pop up. And so from this, we're able to see this blue signal right here. I can zoom in a little. The blue signal is the ideal signal that we have plus noise, and the yellow signal is just the ideal signal, no noise. And so we can see it's a pretty big difference between the two. Over here, I've specified that I only want to look at the positive frequencies. So you can do that by selecting View, Spectrum Settings. Well, I just turned it off, but Spectrum Settings. That'll pop up. And then we can choose all these different things. Here I've just selected to give a start frequency and an end frequency, which is my sample frequency over 2. I'll just set that as 500 for now. So now I can go back to my script, and in order to run this Simulink file, as long as I have it in the same directory as I have my main script, I should be able to run it using the following command. So the command is sim, and then you insert as a character array or a string the name of your Simulink file. So my Simulink file is called Simulink Spectral Analysis. And I'm going to go ahead and save that. And so I can run this Simulink file, and in this out object, it's going to contain all of my output to workspace variables. So I'm going to run that block there. We can see the spectrum analyzer comes up again. I'm going to close that out. And so now we take a look and we see that we have this out variable over here. And if we look into this, we're going to see all these different time series objects. So actual, ideal, all of these. And you can see that in these two workspace blocks, the variable names, they're all named the same as those objects. So this is ideal, actual, spectrum. So what I'm going to plot now is showing the difference between the periodogram, or the averaged power over time, versus a single instance of a power spectrum. And I'm going to do this somewhat manually. So remember, we've used a number of averages equal to 8 and 50 total frames. So I'm going to choose an arbitrary frame here. We'll just pick 30 for now, to show the single FFT. And then what this is going to show in the periodogram data, since we have 8 averages, it's going to show frame 30's power spectrum and 29, 28, 27, 26, all the way down to 23. So it'll show the last 8 consecutive power spectrums that are averaged. So you can see here, and this warning right here actually, until you get up to, in this case, 8 frames, your spectrum will look a little weird, because what it does is it assumes all previous frames have zeros in the power spectrum until you hit this value. So for example, if I were to look at frame 1, I would have read in 1 frame of data, and it would assume that I have 7 previous frames of zeros. And so the amplitude I see will be 1/8 of what I would expect. And then for frame 2, it will have frames 1 and 2 of data, but it will have 6 frames that it assumes are zeros. So my amplitude will be about 1/4 of what I expect. So here on figure 2, we're going to extract the FFT data, and you can see in my model here, where is it? So I'm taking a single FFT, I'm taking the positive coefficients only, and outputting them in this spectrum object. And so right here, I'm taking the output of the Simulink simulation, taking the spectrum object, and I'm taking the data member of that. You can see it's 128 by 1 by 51. The 128 is going to correspond to the number of points for a given frame, or excuse me, half of that, because we're slicing out half the coefficients. So we have a 256 point FFT. So this data will be half of that, or 128 points. And the 51 that's shown there is the number of frames. And so I may have off by one single sample, which is why we would see 51. It might be hanging one sample over in the Simulink simulation. But that number should represent the number of frames that we're simulating. And so I'm pulling the data out from there, and we should be able to see, I'll run this and I'm going to minimize the plot real quick. We should be able to see that we do have 128 by 1 complex double. And so in order to get the power spectrum of that, we're going to take the absolute value of that, or the magnitude, and then we're going to square it. And now for the periodogram data, in order to get this, we can see here that, again, it has the same dimensions as the FFT data, but remember it's taking sort of a running average of the power data. And so if I index this and look at the iframe data, I'll really see an average of iframe and the 7 previous frames as well. And so we can see here, this data is not complex because it's already been taken the absolute value of and squared. And so we can just directly plot that against the frequency axis. And then the last output, so I should have specified this output here is looking at the data which has ideal data plus noise. So we can see the periodogram object. Periodogram shows up here, and so if we follow these traces, the noise and the sine wave are summed together, and then they run through this periodogram computation. And so the periodogram object has the actual signal observed, whereas the ideal periodogram down here only has the ideal sinusoids periodogram. And so in the third thing that I'll be plotting on here, that's going to be the ideal periodograms data. And so if we plot this, we can see here that we have the single frame periodogram, what I'm calling it, which is basically number of averages equal to 1. This is that single FFT that we were doing. And we can see here that the amplitude seems a little bit pretty far off from maybe what we would expect, and we see sort of a lot of noise, a lot of variance in the other frequency bands. But now as we look at the red line, the average periodogram, the amplitude seems to be a little closer to what we expect. So remember, the amplitude that we're using is half a volt, and so if we take half a volt and we square that to get into power, we would expect about 0.25. And so here we're not quite reaching it, but we're definitely closer than the single FFT frame. And more importantly, we can see we don't really have as many spikes in these other frequency bands. What it looks like is that we have a more constant noise level, which is exactly what noise is. Noise is infinite bandwidth if you're using Gaussian noise. So we have more of a flat spectrum here. We don't have as many of these high peaks that can be mistaken as a signal if they get high enough. And now we can see the ideal periodogram, the signal with no noise. Again, the amplitude is relatively close to what we would expect. And the amount of noise in the other bands is basically nothing. So now, really quick, I'm going to address what I talked about before. If I just look at the first frame of this data, you can see here that the actual signal has some amplitude here, but the periodograms have extremely low amplitudes. And the reason for that is we've only seen one frame of data, and it's just assuming zeros for the other 7 previous frames of data, since it hasn't actually seen enough